All right. All righty. Are we good? We're good. Okay. Apologies to the online audience, but you haven't missed too much. Basically, I just made a short introduction of what wall-modeled LES is, and now we're talking about how long it's been in OpenFOAM. And there's been this channel 395 tutorial for LES in OpenFOAM back in the days. I think it's renamed now, but that one did use this wall function. Now, it should be said that at that time, the concept of wall-modeled LES has not been as strictly crystallized and defined as it is now. So I would argue that, the channel 395 wasn't really a wall-modeled LES configuration, but that's beyond the point. We also have a small peculiarity here that we're enforcing the stress by setting the SGS viscosity at the wall. Commonly what is done is instead that you play with the velocity gradient directly, and you basically have a Neumann condition on the wall parallel velocity component. So you get a slip velocity. I think the reason why it's like this in OpenFOAM is purely programmatic, so it just fit better into the class structure or something. So then it's stuck. But in fact, later now we realize it actually has some consequences, and there's now papers comparing the two approaches. This is in a completely different numerical framework, finite differences. So this is actually kind of interesting coincidence that we had something from the 90s and now other people in the 2020s are looking at it. So jumping forward, when I was a PhD student, we built a library for wall modeling in OpenFOAM. It was presented in Exeter first at the 12th OpenFOAM workshop. So I have here the title slide for that. And basically, it adds a bunch of wall models, and it also allows you to set this distance from where you sample the solution arbitrarily for each face, which is, for various reasons, quite important. This is online on GitHub, so you can grab it. It's still being developed, but slower right now because it's not the primary focus of my research. But it's there for you to pick up. So just some selected results. First, the standard first benchmark is always channel flow. So here we have it at a very high Reynolds number, the highest for which we have DNS, at least at the time. Now I think we also have 8,000. And we can see that if we look at the mean velocity profile, we get a very nice result. The stress is also relatively well predicted, less than 2% error. It's worse for the second order statistics, but then it's always an open question of what you should expect for the second order statistics and higher when you do wall modeling. Really depends on who you ask. Some people say you just hope for the best. Some people say we should get it right. We try to do as best possible, right? Then we have also flat plate result. This one is with a more modest resolution, so just 15 cells through the boundary layer. And here we make use of the fact that we can have an unstructured mesh, so we try different types of unstructured meshes. You have one of them here on the picture. And the idea is that we adapt the mesh in all three directions to hold this n over delta equal to 15, even though the boundary layer grows, right? So the cells also grow. And I have just one selected result here for the friction coefficient, and you can see that in all the three different structured meshes we try, we get some good results. So this is to say that for attached boundary layers, I think we pretty much know what we're doing and we're getting reasonable results, okay? So what about separated flow? So that's been in kind of the main thing for wall-modeled LES to try to tackle this for, decades now, I would say, at least 10 years. Johan Larsen from Maryland, he's organizing some very nice workshops on this. There was the first one in 2016, then one in 2022, and there's going to be a next one in 2024, okay? It's a continuous effort, and we have like monthly Zooms on this, and it's completely open. Here's a website. You can go and, you can join every month into these calls and contribute to the next workshop. So what we had in 2022 is this ramp, and basically it follows a setup from an experiment, but a little bit loosely, I would say, but let's say it's inspired by it. So you have this kind of polynomial here, which forms the ramp. And then the participants were told that, okay, you have to fix this Reynolds number and this thickness of a boundary layer at this point. How you arrive there doesn't matter. So you can use your favorite inflow procedure and you can adjust how long this thing is. But at this point, you have to reach these characteristics. And a little bit the same for the outlet. If you want to have a longer buffer region or a sponge or whatever to make your code stable, that's fine. So the grids were actually provided by the organizers. So it was a set of 6 grids ranging from just 4 million to all the way to 420 millions. And you can see that here the different rows are the different participants. So, and if there's a dot, that means that that participant actually ran a simulation on this particular grid. So you see some disparities. Some people just ran on one grid, and for example, their own grid, as you can see, it doesn't fit into either, but size-wise, it was somewhere there. Some participants made more. There was also an effort to do a well-resolved simulation to get resolved data, but that we end up not using it as a benchmark for various reasons. But what did we use? Of course, OpenFOAM, the Whale SGS model. Then for wall modeling, we tried Spalding's law and also a more advanced model based on an OD, which the idea is to incorporate the precedent as well. So that was the main motivation to try it. And then we sample always from the second consecutive cell from the wall. Okay, what about the merit? Well, we know that for a very good mesh, we can just use linear interpolation, and here we could. It was a very good match. But we also know that it's not going to work if we have a more applied situation. So we also wanted to try what is called LUST in OpenFOAM. So it's a blend between a linear upwind and a linear. And we also, by the way, used these PETC bindings for the numerical solver, for the linear algebra solver, which gave us a pretty good speed up on Lumi. So this is just CF and on the different grids in different colors, and then linear and LUST. Okay, so LUST here is solid. And I mean, the main point I want to say here is that the results differ greatly. So it really does matter what you choose. Secondly, what we see here, look here, for example, that on the last 2 grids for the linear scheme, we actually get a more or less overlapping solution. For LUST, we do not get grid convergence. So it really matters what you use. Then now with pressure gradient. So one thing we should look at here is the upstream region, because there is no strong pressure gradient. So the 2 models should give approximately the same result. And we see that occurs only when we're on the good mesh, for example, the M2 mesh. So the red lines, you see they perfectly overlap here in the zero pressure gradient region, which of course is very good, which means that you actually have to converge with your grid so that the models work correctly, okay? So that was maybe a bit disappointing. We didn't get to like a result with our simulations. They're all different a little bit depending on the settings. But to put this into context, so this is just separation and reattachment region predictions from all the participants of the workshop on their finest grid, okay? And we see that there is a huge spread. So not only we didn't arrive to the same result at all. Yeah. And the same if you look at grid convergence, it's the same. So we want to kind of plateau here, but nobody plateaus. So you refine the grid, but the location changes. So the conclusions are that we have very strong capabilities for wall modeling in OpenFOAM, perhaps the strongest among general purpose CFD codes. We know how to deal with attached boundary layers. For separated flows, the whole community has work to do. Okay, we need high Reynolds data because right now it's very scarce. We show that numerics are very important. We have to push and squeeze everything we can out of our finite volume method, and pressure velocity coupling, all that stuff. We really need, because it matters. Thank you very much. Yeah, just linear interpolation between the cell centers. Say again? Yeah, so let's say when I was running those, I wasn't aware of that. But that was a good option. I mean, it's a trade-off because you preserve energy, but you also lose second-order accuracy, right? So, yeah, it's also worth mentioning that there's now the solver released. It's RK. It's a Rugikoda-based solver, but also with some nice improvements. It's from Barcelona, so I want to try that as well. I don't think they made a submission. There are people in the calls. So Lozana Duran, for example, Jane Bay is in the course. She's no longer Stanford, I guess she's Caltech, but she's, well, from the CTR origins, let's say. Yeah. This is the main difference for the main advantage of warm-up, I guess, is that we are the project. Yeah, so the main difference is that if you use HYDRODYNAMIC, I mean, at least economically, that's how it started, is that you treat the whole boundary layers around, right? So here we treat only the inner layer as the Ivers around, as previous Wolfsburg modeling. So it's a mobility method compared to a hybrid LES round, but it also costs a lot more, of course. Because, for example, a flat plate with a hybrid LES rounds, it's a round, right?
Especially because of the should be used to reduce almost some of the geometry research will depend on the geometry of the
Yeah. Well, so there's always the problem with this coupling between the unsteady solution you sample and put into the wall model, and the fact that the wall model is essentially written for a mean flow, right? Yeah, somehow either you just say, okay, I'm just going to use a transient signal, or sometimes you average the signal to make it more compatible with the wall model. But in principle, the issue remains. You are using an average equation, or some people just use full-blown Rance equations for the wall model. But still, it's for an average flow. So it's no way around it. The idea, I guess, is that that the inner layer is so fast in its dynamics, the time scales are so small, that if you are at a high Reynolds number, then each of your cells is huge in Y plus units and in Y plus time units. Your time step is huge in plus time units. That justifies the fact that you can consider everything in the inner layer in an average sense. So whether one buys that or not is
next step will be to
I mean, it is unsteady, right? Because we're not but almost everything is unsteady. I mean, because you have the whole number there, which it is completely unsteady. It's only the inner layer which you. Yeah.
Okay. So thank you again, Victor.
Okay, so main advantage of immersed boundary methods is that you don't need to do complex meshing. But a big downside is that your fluid flow interface is a bit ugly. So in today's presentation, I will talk about turbulence modeling that is very sensitive to the quality of the fluid surface interface and how we are trying to do it with immersed boundary. But at the beginning, I will say why we are even concerned about this. In our research group, we are developing a code that can be used to simulate moving particles with arbitrary shapes. The code is open source, you can find it out. But this code, we focus on arbitrary shaped particles. So our particles are represented by polyhedrons, and the shape of the particles is fully resolved. So the coupling between CFD and DM part is very, very strong. And all in all, the method can be denoted as particle resolved direct numerical simulation. And the direct numerical simulation part is the problem, because we would like to use our code also for simulations of large objects like propellers and so on. And that's the reason why we want to use some turbulence modeling that is cheaper to simulate. So what we had available, we started with our custom immersed boundary method that is able to do the simulations with moving particles. And it is implemented in OpenFOAM. And on the other side, in OpenFOAM, there are implemented the tricks regarding Reynolds averaging. And our goal was to create a hybrid that uses modified the immersed boundary method and the turbulence models and wall functions from OpenFOAM. So I will just try to briefly describe the method as it works. And when we start with the immersed boundary itself, then when you have some finite volume mesh and you want to project a solid body onto it, then you can project it using a indicator scalar field, which gains values from 0 to 1, where cells with 0 are in fluid, cells with 1 are in solid, and these cells form the fluid interface. Then, based on the indicator field, we can further divide the cells into insolid cells, boundary cells, and free stream cells. Now, regarding the indicator field, it's very important because it carries the information about the geometry of the solid, and basically the cells that the interface, the value of the indicator field is computed from a standard distance, which we know, we have the SPL of the solid phase, and thanks to that, we can then, in the simulation, reconstruct from the both scalar field, we can reconstruct the surface of the body pretty precisely. So that's the importance of the geometry indicator field. But what about the division of cells? This is important for the governing equations. And as I said at the beginning, we are interested in Reynolds averaging, so we use this type of equations where the effect of the solid body is implemented in this source term, which is a forcing term that simulates the effect of the solid body on the flow. And it's computed from immersed values, which are then enforced by the iterative solution in respective cells. And you may notice that the Coarse term is not active in the whole domain. It's always 0 in free stream cells, and it's always active in the influent cells. And in case when we have resolved by the boundary layer, it also is active in the boundary cells. In case when the boundary layer is unresolved, we just let the flow behavior be governed by the turbulence viscosity. In turbulent viscosity, we focused on 2 equation models. We implemented 4 of them, and I will just describe the implementation of the K omega model, which, as you probably know, the K omega model adds 2 more conservation equations to our simulation, where the conservation equation of turbulent kinetic energy was modified. Also in the source term, which simulates the effect of the solid body, and it's computed in the same way as the source term in the momentum equation. Then the equation for conservation of specific dissipation of K, we did not modify this equation, but instead we used some matrix manipulation to enforce the immersed values inside our solid body. And you may notice that when the boundary layer is resolved, only the omega immersed values are important. Yes, so the key to have a successful simulation with immersed boundary method is to correctly set the immersed values. So how to do that? Basically, in the solid cells, the yellow cells is easy because we know the boundary conditions. We know that velocity goes to 0 when the solid is not moving. When it's moving, it's the velocity of the solid. We know that K goes to 0 and omega goes to infinity. So we can just prescribe those values in the yellow cells. That's easy. More of a problem becomes in the boundary cells because, as you know, when you have turbulent flow, the boundary layer thins out. And normally you can solve this by making the mesh finer near the wall. But when you have immersed boundary, there's a problem that the mesh is not aligned with the wall. So if we would like to do something like this, we would not need to make it finer in all the directions at once, which is very costly. And also, if the image boundary will be moving, we would need some adaptive mesh refinement, which is even more expensive. So that's not what we want to do. We do not want to work with this kind of mesh, but of course we need to specify some physical exceptions. So that is normally solved by wall functions, where just simple functions like algebra parameters that are used to so based on one class that is computed from perpendicular distance to the wall. When the forms of wall functions we use are just these that split between two different formulations, one for viscous tubular and logarithmic region in the switches in about 11y plus. But what is more interesting regarding the image boundary is how to compute the perpendicular distance, because you don't have there the wall. But this is why the geometric indicator fields is so important, because from this we can construct the sign distance, and using some geometric parameters from the mesh, we can compute the perpendicular distance. So we can use wall functions. So, and to conclude the wall functions part, omega, it's simple because wall functions for omega are designed in such a way that they return a value. We just use it simply as it is. For the wall functions, there's more of a problem because usually the value is used to prescribe a direct boundary condition at the wall, but we don't have their wall. We can't prescribe the direct boundary condition, and also it's we can prescribe direct boundary condition. So what we use is some kind of interpolation, where we interpolate between values in the free stream and the value at the surface that we know from the direct boundary condition, and we interpolate just using some polynomial to acquire the value in the boundary itself. So like this, we can acquire the inverse values. And the last thing we needed to modify was to do some minor changes in the solver iteration loop. Here's just a simplified version of a simple algorithm where first there's the implementing predictor step, where we added some posterior correction and inner iteration loop to enforce the inverse values. Then there's the pressure corrector step there, it's the same. Then there is still the omega equation, where after the discretization, the matrix manipulation takes place. Then the omega equation is solved. Then the solver goes to the k equation, where once again we have a posterior correction and inner iteration loop. And well, the reason why there are those iteration loops is just for stability. It does not affect the solution. So like this, we can compute Reynolds average simulation with inverse boundary. And I will just show you some verification and validation test results. So first, we started with just simple pipe, where we compared always simple foam with our solver, and we compared here the velocity profiles on the Z line over there. And you may see that for different Reynolds number, the accuracy is rather acceptable. Only there are minor differences in the middle range Reynolds number. When we look at the turbulence viscosity, the difference becomes more visible. This may be because we are in the mid-range Reynolds number, there's a problem with the buffer layer, so that's a thing we're going to work on. But in the low and high Reynolds number, it works well. Then we try to test it on some band meshes, where also we compare the velocity profiles, and they came up acceptably accurate. And also we compare the turbulence viscosity profiles, so same case. And the last case I will present you is a validation case where we use the vector set benchmark the experiment data. And at the top right, there is a solution from simple foam, and beneath it, that's our solution. And you may notice that we predict a bit thicker boundary layer, which is the one of problems of our approach, but we are working on it. But when we look at the velocity profile along the whole channel, the differences are not so big. So we are satisfied with the results. And if I conclude, we have some simulation code that can do Reynolds average simulation with immerse boundary method, and it's available. It's open source, and it can run stable run simulations with acceptable accuracy. But there are some flaws that need to be improved. And in future work, we would like to merge it with our main branch at the movement, the particles moving, and also do some further verification and validation. And lastly, implement also the LES and maybe GES approaches. Yes, just for me, it's references, and I thank you for your attention.
Yes.
It's OpenFOAM 8, openfoam.org.
The validation, the simple form case, it's not clear for me that it was simple form with a buffer or on another view.
Yeah, it was like the grid was made to be so similar as possible.
Okay, so standard simple form.
Yeah, standard simple form. Yeah.
I don't know it's already this is still required and that is you also have an underground just giving away different from one to the ports at the regular markets.
Yeah, that's true.
So in principle, you could also have a straight mesh with the boundary and
yes, but when the immerse boundary is moving, we would need to like review it every single time, which is like costly.
in that case you should somehow match it. So you want to more okay. That's me. So is there another question? Just to let me remember the second question. No. Unfortunately.
Yes, we are planning to do that, but yes, that's true. But one of our colleagues are working. They are simulating a riverbed where they are moving rocks, and like riverbed is like 100 meters, and the rocks are like really big. And there still is like chance to be better to use the Reynolds average simulation because the rocks are big, and you don't need so fine mesh to resolve the shape, but you would need much finer to do the direct numerical simulation. Yes.
I remember the question. In your test, you tested essentially steady flows, right?
Yes.
I guess that if you just a steady flow, that's probably more than just for I mean you just change quantities in giving. So you could also weigh so it's essentially it's like an infinite iteration method. So it doesn't mean that you correctly simulate the problem solution. You can time.
Yeah.
So since you essentially the method you are just the fourth step in momentum equation, you should be sure that that quantity is is correctly computed.
Yes, that's true. But well, we. It's like we finished it quite recently, so there wasn't enough time to do it. It was okay. But you're not.
I have a question. I want to be thank the speaker.
Okay. Yeah, I'll start now. Hello.
Okay,
Yes.
so please.
Okay. So, yeah. Hello, this is Lubna Margha presenting turbulence modeling approaches for the hydrodynamic analysis of floating offshore wind turbine under supervision of Professor Windon and Professor Germagi. The outline of this presentation starts with motivation, then introduction is discussed, followed by stating the objective, next model description, and is presented, followed by results and discussion. Finally, conclusion are presented. So as a motivation, floating offshore wind turbines are desirable because they access deeper waters using stronger winds, offer scalability, and provide economic opportunities. They expand offshore wind potential and meet growing clean energy demands. The subsystems include the aerodynamics and turbulence on the blades, hydrodynamic floating platform, mooring systems, turbulence structure, and control system, which work together to harness wind energy in deep waters. Floating offshore wind turbines face several hazards, including severe weather conditions such as storms, high winds, and large waves, currents, and tides, ice impacts, which can put stress on the turbine structure and its mooring system, besides the turbulence, wind, and wake turbulence on the blades. To take care of all of these hazards in numerical simulations and simulate this severe turbulent weather, we need high-fidelity CFD tool. There is commercial and open source industrial software like OpenFast and StarCCM, but they depend on the Morrison equation and beam element method, which are low and moderate fidelity CFD. That's why most recent simulations of fluid-solid interactions are investigated using the OpenFOAM software that's high fidelity CFD. So starting with turbulent modeling, the RANS methodology is computationally efficient but limited in capturing the full range of flow physics coherent turbulence due to its one-point closure approach. DNS and LES techniques provide accurate computations but may be computationally overwhelming for
We don't hear you. Wait a moment. Please try the connection.
Maybe she don't have internet.
range of scales.
Okay.
Large-
Now we hear you. We left last 30 seconds. So the connection was unstable.
Okay, so let me repeat this slide again.
Exactly,
So,
this slide again.
okay, so talking about the turbulent modeling, the RANS methodology is computationally efficient but limited in capturing the full range of flow physics coherent turbulence because it's the one-point closure approach. DNS and LES techniques provide accurate computations but may be computationally overwhelming for applications in aerospace and ocean engineering. So to distinguish between URANS, LES, and DNS, URANS focus on mean features of turbulence that average everything. LES presents large and medium coherence turbulence scales. DNS results in the whole scale of turbulence. So it's always compromised between accuracy and computational power. And the question here is which level of complexity should be selected for our problem. The turbulence relies on a wide range of scales. Large scales are where production is generated and it cannot be modeled. Medium scales or inertia scales are difficult to be modeled, but it can be. Small scales are where dissipation happens and it's the easiest part to be modeled. Any turbulence quantity can be decomposed into mean, coherent, large, and medium, and stochastic small turbulence. When we add coherent to stochastic, we get the fluctuation field. So when we focus on the mean only, we get the RANS by modeling and or averaging the whole scales. When we resolve coherent, large, and medium, we get LES. When we resolve all scales, we get DNS. Another decomposition can be done by introducing a filter which divides the domain into resolved or filtered field and unresolved or residual field, and this is done by bands. So an example of the bands is that if the filter is 1, this averaging everything gets RANS. Decreasing the filter value means resolving more scales, reaching to resolve all scales at fk equal to 0, which is DNS. So, talking about the RANS realizable K epsilon model, it's a relatively recent development and differ from the standard K epsilon model in two important ways: that it contains an extra formulation for turbulent viscosity nu T and CMU that varies depends on the value of nu T. It's not a constant like the standard K epsilon. And the transport equation for the dissipation rate has been derived from an exact equation, and also the realizability condition that avoids the unreal negative eigenvalues on the Reynolds stresses is a very good advantage of this model. So here also from the Wolf Dynamics training about the multi-phase flow using VOF method 2021, they stated that using the primary phase properties to compute the turbulent quantities is recommended, and it is also common in literatures to use only the primary phase as a reference. So, but we found that we have to set boundary condition, initial condition for each phase separately, and that will be presented in the results shortly. So stating different turbulent boundary condition, initial condition for each phase, starting with the eddy viscosity, which is a ratio of the kinematic viscosity of each fluid, we settled it as a coded fixed value depending on the VOF equation at the free surface. Then the internal field is settled from the set fields options for the alpha water, eddy viscosity, and epsilon value, which depends on the value of nu T. So our objective here is to compare different turbulent models like RANS, standard K epsilon, realizable K epsilon, and scale resolving bands K epsilon on predicting the hydrodynamic forces on just a simple geometry like suspended fixed cylinder interacts with regular log waves. Our investigations also include the effect of using different boundary and initial conditions for each phase, depending on the physical viscosity of each phase. Simply, the comparative study among high fidelity various turbulent modeling techniques is applied to a suspended cylinder as a validation process involving comparing the model's results with available experiment data. The test involving a regular wave interacting with a suspended vertical cylinder with a diameter of 0.2 and aspect ratio of 7.2. Selected wave characteristics are a wave height of 0.37 with period 1.533 and wave depth h of 10 meters. So the grid design of the domain shown is clustered with different refinement levels to simulate the wave. Furthermore, the grid is clustered around the cylinder with 5 levels to capture the turbulence. Boundary condition wave as outlet is shallow water absorption, and the grid design allows the wave to dissipate after the cylinder to avoid the reflection effect on the cylinder. So starting the results with the ransom standard K epsilon turbulent model using single eddy viscosity on both fluids depending on the primary fluid water and CMU constant 0.09 that standard K epsilon does. So the hydrodynamic forces on the cylinder become so dissipative as this model add artificial viscosity from Boston-Nazca approximation, which dissipates the wave and reduce the value of the commutation Reynolds number. Taking the advantage of the realizable K epsilon model that CMU varies with nu T but still using the same single eddy viscosity that depends on the primary flow water in both fluids, we got the result that better than the standard K epsilon but still diffusive. Investigating the bands K epsilon model using filter value of a little bit high FK 0.7 and single nu T as ratio of the water kinematic viscosity, the results enhanced than RANS models, but still couldn't capture the accurate forces on the cylinder. So reducing the filter value of bands 0.2 and using single nu T on both fluids, that results got an amazing results accuracy to capture the hydrodynamic forces correctly. So trying to repeat the simulations using different nu T for each phase, starting with standard K epsilon, we found that the results enhanced a little bit than using single nu T for both fluids, but still diffusive. Investigating the realizable K epsilon with different nu T, that we got a wonderful accuracy to capture the forces on the cylinder, with just the difference using just different nu T for each phase separately. So using the same mesh and same computational power that all the simulations were computed using the Grace cluster of Texas A&M using 4 nodes and 48 processors per node. We see that bands of small fk.2 using single NUT and the realizable k epsilon rands using different NUT for each phase were the most efficient turbulence models to capture the hydrodynamic forces of the suspended cylinder correctly without any dissipation. So as a conclusion, there are different turbulent techniques to simulate wave propagation and wave structure interactions. One of them is using the bands turbulent modeling with fk.2, and this is because bands decrease the portion of modeled scales and resolve the coherent structures that decrease artificial turbulent viscosity. The second is using the realizable k epsilon rands turbulent modeling with different eddy viscosity for each phase, and this is because that the realizability condition avoids the unreal negative eigenvalues in Reynolds stresses, and the multi-phase flow have a huge difference in kinematic viscosity. This changes the turbulent behavior between the two phases. Thank you for your attention. Questions? Hello? Yeah.
Super efficient. So we have time for questions. So please, I think that you should come and actually make the question because otherwise.
I'm so sorry, I can't hear the question, so I would appreciate if the moderator just repeat it again, please.
Wait.
Yeah, I'm coming to. Can you hear me? Can you hear me well? Hello.
Yes.
Good. Yeah. So my question is, how do you in the end select this? What is it called? FK for pants. Because you try 0.7, you try 0.2, and 0.2 kind of worked well, but can one somehow a priori know which value to select?
Okay, I think you have to simulate each different values to select, but I started with fk.7 that it's very close to fk1, like it's not resolving everything, it's just resolving little bit of the coherent and modeling the other. So 0.7 that gives me enhanced results, but not a very good results like I want. So I try to state like 0.2, it's close to the DNS and LES, so it gives me very good results. I also trying right now to using fk.5 to see if it's in between 0.7 and 0.2 what will happen, but this is research in progress.
Okay, thank you. Can I have one more? Okay, so but then as a follow-up question, but do you run on the same grid for all of these FKs, or should the grid be changed?
No, it's the same grid, and it's very refined near to the cylinder. And the mesh is like 1 million, 1.3 million cells.
Okay, thank you very much.
Yeah, thank you.
Next question is coming.
Hello, can you hear me?
Yes.
Okay, so I have 2 questions. So I have tried PANS for a similar case in OpenFOAM, and my first question relates to that you start with FK as 0.7 and 0.2, but when you look at the end of the simulation in ParaView or TechPlot or the post-processing software, do you see that the same FK is maintained throughout the simulation, or does it keep changing in some regions or in some time steps?
I use FK for the whole domain, the same FK.2 for the whole domain. It's not using hybrid for different meshes like the hybrid LES and RANs. It's just FK fixed for the whole domain.
Okay, so I am assuming at the end of the simulation, throughout the domain, FK is 0.2. It does not change according to the wall cell size, because PANS is supposed to be a bit grid dependent, right?
Yes.
Okay. And my second question is, when you start PANS with the with FK is 0.2 or 0.7. There have been some studies by Dr. Girimaji himself that they start with running a full case run simulation and they use that field data to start the Pans calculation. Is that the case here, or this has been started with no calculations at all, like no input data from any other runs calculation?
No, I calculated everything before starting. So I first started with RANS, and then I calculated the coefficients for using bands with a certain FK and settled it on OpenFOAM. Then I got the results. This is your question.
Okay.
Yeah.
Yes. So it is. So it is dependent on the turbulent length scale. Then I'm assuming.
Okay, turbulent length scale. I think this is not the case here. Just trying different FKs and calculated the coefficients, but we just settled the delta X and delta Y on the cylinder itself to be fitted with the FK used. That
Okay.
it's very small. Yeah.
Okay.
To
Okay.
capture.
Thank you.
Thank you.
Thank you.
What kind of turbulence structure do you refer to? Like from the political viewpoint, maybe not scale motions or you know? So depending on the model, but more focusing on the turbulence feature.
I didn't hear this question. Please, can you repeat it?
And what kind of turbulence structures do you refer to?
What kind of turbulence
structure did you observe?
I'm sorry, can you repeat it?
What kind of turbulence structures do you refer to? Like very large scale motions or near wall structures? What can you?
We focus here this study on the hydrodynamic forces on the cylinder itself. So our next phase of this simulation, we try to study the turbulent properties like the Reynolds stresses and K epsilon. I'm sorry, K epsilon. Yeah, other turbulent. Yeah, K epsilon over omega, not omega.
So it's the result of your future, essentially. Okay, I understand.
We just we're interested in the application itself and seeing the hydrodynamic forces because all the literatures that using the Morrison equation and potential flow, they got a very high results. Not accuracy, but the time is very small. If the computational times there's very small, but there are a lot of dissipation in using the RANS and the potential flow. So we try to avoid this dissipation by using bands and takes advantage of the realizable K epsilon. And when we try the realizable K epsilon and it's also dissipative, so we try to set up different nu T for each phase that each phase, the kinematic viscosity of water and air are very different. So nu T would be a ratio of the kinematic viscosity, and it would be very different between the two phases. And to set the continuity on the free surface, we set it like nu T as a function of the VOF equation, and that we got our results.